Hi, I'm Nicieza, and today I'm going to be talking about the design of high-frequency magnetics and how to optimize the process. If we look at the process of designing a magnetic component, it generally looks like this. We have an engineer that needs to look for an optimum solution, and there is a huge amount of possible designs that could be used. Now there are two options. One is that this engineer goes and does his or her own spreadsheet, or a second one, which is he can go for a software that can provide an optimum solution or that can run a certain solution. Now the reality is that the engineers like to take decisions, and engineers need to know why an optimum solution is an optimum one and what are the trade-offs taken in the design. The better this occurs, the better control the engineers will have on their components. So one of the ways to really optimize the process of the design is to split it in three parts. In the first one should optimize the selection of the core. This is one of the most important ones because it's going to determine the size, it's going to determine the power density of our component, and it can have a huge impact on the cost. Then we have to optimize the winding arrangement, the selection of the wire, and finally how the windings are going out, how the component is attached to the rest of the system. So it is critical to take the right decisions in each of these processes and to understand the trade-offs. And today I'm going to show you how the core could be optimized. So I'm going to Frenetic Online, and here I'm going to show you an example of the core optimization on a phase shift full bridge transformer. We have a 500 watts phase shift full bridge transformer with a magnetizing inductance of 500 micro, a switching frequency of 100 kilohertz, an input voltage of 400 volts, an output current ripple of 2 amps, a power, as I said, 500 watts, turns ratio of 5 to 1, 48 volts, battery output, 500 watts. Now, here we have the voltage and current across the primary and secondary windings, and now we need to select a core. And how to do that? We have done what we call the core optimizer. What we need to define is what is our core loss target and how to come up with this value. If we think on a power converter, we have an efficiency target. So this means that if I want to have a 95% of efficiency, I can lose 25 watts if my converter. Now, as a rule of thumb, and this depends on the application, but as a rule of thumb, we can take 1/5 or 1/6 of these losses in the complete system for my magnetic component. So if I divide 25 watts by 6, this means in my transformer, I could lose up to 4.2 watts, more or less. Now, if we think of magnetics, and again, it depends on the application, ideally, the core losses should be half of the total losses, and the winding losses should be the other half. So this means we can consider as a starting point half of this to be the core losses, so this means 2 watts. Now I can get back here, I can define my core loss target is 2 watts, and I can select a family of cores. Like for power, we can go for a PQ, for instance, and a material which at 100 kilohertz, we can go for a 3C95. Now, what we have here is in the y-axis, we have the effective volume of the core, and in the x-axis, how many turns do we need with that particular core to get the losses that we wanted. For instance, here we have a PQ50, it needs 20 turns to have 1.98 watts. This is the flux density in the core, this is the power density, and this is the total volume of the component. So of course, if we increase the number of turns, we can come up with smaller components that has much higher power density. So here in this graph, we can very easily analyze many different cores and compare them, how many turns we will need, because we know that the bigger the turns afterwards, the higher the winding losses. And we can compare different families. For instance, I have some the PQ, but we can also plot an ETD or an E-core or whatever family. We can compare and see what other cores are available in the market and what number of turns do we need in each of them. But now let's say I have decided that the PQ35 is a good option because the power density is intermediate one. It's going to be a good one for my converter. I can go for the core loss versus number of turns. And what is this curve? Here what we can do is a more extensive analysis. So if I pick again any core, in this case I'm going to pick the PQ3535 as I said before, and the 3C95 material. What I can see is how is the evolution of the losses with the number of turns in this core. So I can also know and take trade-offs when it comes to the winding. If I go for 20 turns, for 25 turns, for 30 turns, when it's going to be the impact in the core. And it's not only that, but I can now check different battery levels. So if my output battery goes up to 60 volts, now what happens here is that I'm going to have more voltage across the transformer. So therefore this means that for the same turns I'm increasing the losses up to 3.2 watts. In the same way, we can change any input. So what happens if we go for 200 kilohertz? What is the impact? This means that my flux in the core is going to be much lower, and therefore now I can go to almost 1/3 of the losses. So at the end, with this optimization of the core, what we can do is analyze many different options and many different materials. What happens if instead of this 3C95 we want to go for instance 3C98? What happens in principle is that it has more losses. If we compare one by one, it would be this curve with this curve. Now the thing is that this material is optimized for high temperature. So this means that we should increase the ambient temperature. So if we increase here to 80 degrees, then if I run again, what I will see is that the losses of this 3C98 are much lower. So here we can compare many different materials, many different conditions, and take the right decision on the core before continuing with the winding. So I'm going to go back to the 25 degrees ambient temperature, and now I'm going to select the PQ35 with 25 turns, which is the one that fits my application better. That's how we can really understand different cores, take decisions, and then we can continue with our design. Once we have the core defined, we can just continue with the winding and then finish the design and have a product. And of course, because we know how this has been done, or how the selection has been done, if we now need to change any input specification, we can easily see what is the impact in our core and take the right decision after that. That's it. I hope you enjoyed.